All right, we're going to talk about projectiles, specifically in the context of the basketball video analysis that we did. Turns out I don't know basketball, and that probably doesn't surprise anybody. Looking at a projectile. So in our basketball lab, we saw a person, you threw a basketball, it went up, it came down, following a very typical sort of parabola of motion for a projectile. A projectile is pretty much any object which has been projected with a force and becomes a projectile sort of once that force disappears. And the only thing that's really affecting a projectile for its motion is gravity and air resistance, but we're going to ignore that for now until we have a good grasp on everything, and then maybe we can circle back and think about the effects of that. So the basketball becomes a projectile once it's out of the guy's hand, it's been projected, and it's just sort of following the path based upon what velocity it has and what's going on in terms of gravity. When we look at that, it seems kind of complicated at first to really understand what's going on, because at every interval, and on my diagram we'll say that each drawing here is 1 second apart, at every interval the velocity seems to have changed, not just in how fast it's moving, but also the direction. And the reason for that is because when you throw a projectile like that, as you know, it's moving horizontally in the x direction, but it's also moving vertically in the y direction. And when you put those two things together, you get that parabolic arc. So what's going to help us and allow us to do any sort of calculations on this is we're going to break this into x and y motion. We're going to take this diagonally moving thing and break it down into how is it moving horizontally, how is it moving vertically. And when we do that, you'll see first off that our X-Monster and VATVO and the timeless equation, the equations we used way back when, are completely still applicable and allow us to assess not just how is it moving horizontally, but also how it's moving vertically, and then that lets us put together the bigger picture of sort of at any given moment, what's it doing? Is it moving diagonally up? Is it just moving horizontally? Is it moving down? Whatever's going on. So to do this, we're going to start with looking just at the x direction. And to do that, I'm going to take our projectile motion and I'm going to sort of squish it flat. Okay, so this would be kind of like you have a bird's eye view of this projectile going up and coming down. Like from a perspective way up above, you wouldn't really be able to tell how much it's moving towards or away from you, so you'd really just see the projectile kind of moving horizontally. And right away, because I said each of these is at an equal time interval, right away when we get rid of the y component, it should sort of stand out to you that the ball has moved sort of a set amount every given second. And so what that tells you is that we actually have a constant x velocity. And the reason for that is because we're ignoring air resistance, right? So in terms of horizontal, once a ball's out of your hand, if there's no air slowing it down, then what would change its velocity? Nothing in this case. So it has a constant velocity in the x direction. And so what that means is figuring out things like displacement, piece of cake. If it has a constant x velocity, then every second in this case it's going to be moving 5 meters. So 0 meters, 5, 10, 15, 20. Again, that's because we're ignoring air resistance. If you actually go outside and throw a basketball, or depending on how careful you were with your clicks on the video analysis, you may have noticed an acceleration component for the x direction, and that's likely due to the fact that the ball has to push air out of its way, and that's force and therefore acceleration, and it does have a meaningful effect in the real world. So in this case though, we don't have that, so we just have it moving 5 meters every second. So let's do the same thing from the y direction. In this case, it's a little trickier because we know this thing doesn't just move up and keep going until it's in space. It actually does come back down. So when we squish this and consider the y direction, we have to consider the fact that this thing is moving both up and then also back down. So in this case, what do we know about this? Well, one big thing that we definitely know is that there's gravity pulling the ball down, and gravity's constant, and gravity is always down. So negative 9.8 meters per second squared acceleration towards the ground. That's affecting it when it first leaves the person's hand. That's affecting it when it's at the top of its motion, and that's affecting it when it's back down to where it started as well. The gravity acceleration is constant and always down. So just make up a number. I'm going to pick 29.4 because it works out really easy math-wise. So if I say that this thing initially had a vertical velocity of 29.4 meters per second, then I know that 1 second later, its velocity should have gone down by 9.8 because that's what acceleration is. It's how much the velocity is changing per second. So this thing has decreased its velocity by 9.8 or accelerated in the negative direction. 1 second later, goes down by 9.8 again. 1 second later, we're at the top of our arc. And now it has a vertical velocity of 0, which means for a split second, this thing is no longer moving up, and it's not yet moving back down. It has reached that sort of pinnacle of its motion, that apex point. And that's an important thing to recognize because that would be sort of the time at which this is at its maximum height, which might be a thing you care about when considering a projectile. Now, the acceleration doesn't just go away, right? It doesn't just stop there. That'd be cool, but that's not how it works. So if it's at this 3 second mark, 1 second later, the velocity is just going to continue to decrease by 9.8, which in this case means that now it has a negative velocity of 9.8 and a negative velocity of 19.6 and a negative velocity of 29.4. Just to sort of take stock of that again real quick, what that means is that we started with a positive velocity of 29.4, went to 19.6, it went to 9.8, it went to 0, negative 9.8, negative 19.6, and then back to negative 29.4. So the difference from the beginning to the end of this projectile's motion is just that initially it had a positive y velocity of 29.4, and when it came back down, it had that same velocity of 29.4, just in the negative direction, which is part of the reason why when you throw something up, you want to make sure it doesn't crack you in the head. Also probably why you don't get a bow and arrow and just shoot it up. It kind of seems like a cool idea. Don't do it for like physics reasons. So that's the vertical motion. Putting these two things together, you see the x velocity constant in the direction to the right. The y velocity starting positive, becoming less, 0, and then continuing to become less, more in the negative direction. And just a quick note, it seems like something has changed at the middle here because we went from these positive velocities to the negative velocities. But remember, your acceleration versus time graph for this would just be a constant negative 9.8. So this thing, nothing's changing in the middle here. All that's happening is you get this constant change in velocity, and you just happen to cross over from positive values to 0 to negative values, but it's all very smooth, constant acceleration. When we put these two things together, now we can appreciate sort of the overall motion of this projectile. That this thing started with this positive horizontal and this positive vertical, and so it moved in that diagonal direction. And if you look at this, you can see the vector of these two vectors added together to create this diagonal motion. They have this x velocity that's positive, this y velocity that's positive, and so you have this up and to the right velocity overall. 1 second later, you see how the overall velocity is starting to flatten out because we have less of a vertical component. 1 second later, less of a vertical component, starting to flatten out even more. At 3 seconds, completely flat. There's no y velocity. It only is moving in the x direction. 1 second later, now we start to get that negative y velocity, and our overall velocity vector begins to point downwards, and then more downwards, and then more downwards. And so when we consider projectiles, we need to break them down into what's happening in the x direction, what's happening in the y direction, because then we can apply our kinematic equations. There's no kinematic equations, or not ones that you want to use, that will take into account both the x and the y directions at the same time. So we'll have to use the clues of what's given to us in the scenario of the projectile. Is it something like throwing the basketball? Is it a golf ball being hit up and in the positive directions for both x and y, or is it something that's just being thrown off of a cliff, in which case then you might have a different scenario in terms of where did you start vertically and how much velocity did it have. So it's going to be important for us to break down the projectile motion into x and y, and once we do that, it should be totally just old hat, the things we've already been able to do in terms of the kinematic equations, and it's just sort of in a new lens, a new way of looking at this. Okay. that's an intro to projectiles.